A very warm welcome to you all. In this video I'm going to demonstrate how, with the Hvac CFM simulator module, you can carry out an aeration ventilation simulation. We are now activating the temperature and humidity module. This module allows us to perform calculations that account for heat accumulation in the building's partitions and its internal equipment. For this purpose, I have already prepared a specific calculation file, which I am currently opening. The investor's primary objective here was to ensure that the temperature inside the hall did not exceed 32 degrees Celsius. This was crucial due to the specific technology being utilized within the facility, which operates as a high bay warehouse, fully automated. And I won't go into detail on how to input this data because it's already been described and thoroughly covered in another video, specifically the one accessible via this very button, which covers a full overview of all these program's features. This video is a bit dull and lengthy, but it does cover all the relevant topics. However, for the purpose of this video, I'll just mention that we input the room and equipment dimensions. Here we provide parameters for external partitions, or perhaps not only external, but generally for all partitions of this room. Its heat transfer coefficient, surface area, and so on. Here we define the time-dependent variables that are present within the room. And in this scenario, we have a situation where throughout the entire day, there are constant heat gains from the equipment in this room amounting to 50 kilowatts. We have no moisture gains because it is a fully automated technology. And we have a minimal ventilation airflow, which we require for what we might call hygienic or technological reasons, 6,000 cubic meters per hour. But would this be enough to maintain the temperature in the room below 32 degrees? We'll find out soon. The calculations are being performed for a specific facility which is located and situated in Poland in the city of Opole. These calculations, because our primary interest is the summer period and maintaining a maximum temperature of 32 degrees Celsius there, are conducted for the duration from May through to the end of September. And here we select the computational mode for the temperature and humidity of the supply air, which is equal to the parameters of the outdoor air. Now, regarding the input of partition parameters, we see on this diagram it's a cuboid, but in reality our room could have a slightly different, more complex shape. I'll explain that now. For this, I'll delete it and show you in a moment. For a room model of this particular type, which we can assume is significantly more complex, we are able to implement a certain kind of simplification, which means that if we take a closer look at this situation, we will notice that both this section and that section of the wall is a wall on the northern side. This segment and that one are located on the southern side. Then over here we have another one situated on the western side. However, these three sections are positioned on the eastern side. Therefore, we can represent this using a simplified diagram simply by shifting them, these walls, into the position they should occupy relative to the cardinal directions. And in this way, we actually obtain simplified representation of this room, which, as you can clearly observe, is shaped like a rectangular prism and is being analogously introduced into this very specific field. Now here we also note that if we happen to have several windows within a particular partition, we simply input them as one single cumulative window for that specific room. All right, that concludes all the additional explanations we needed to cover. We are now initiating a simulation for our specifically defined schedule of internal heat gains and fresh air supply, and we are carefully observing whether we will be able to successfully maintain a stable temperature of plus 30 degrees Celsius within the room. A maximum of 32 degrees, and here we can already see that we have exceedances in certain periods. So if we are to guarantee something to the investor, unfortunately we will not be able to achieve this by using only standard residential ventilation. Here we even have, excuse me, we even have a situation where this temperature reaches 35.5 degrees. Outside it might be 32.9, but due to internal heat gains and gains from for external partitions, the temperature will simply be higher. And so now, as we move on to our time-dependent variables, we need to utilize the potential of the outside air, because as we can clearly see here on the chart, throughout this entire period, we have a situation where the temperature of the outside air is quite low, and this effectively allows us to achieve free cooling. We can also utilize the accumulation of this cold in materials stored inside the warehouse and in the partitions themselves. Of course, if the partitions are massive and allow for it, it's not always possible, but the floor and equipment certainly are. So we can establish a system where during the nighttime hours, when the outside temperature falls below the internal temperature, specifically the room's temperature, we can then use this cooler air for effective cooling. Therefore, I've already run these simulations here, so I know what values to input. I'm entering 100,000 cubic meters per hour that we will be providing during the night period, from basically 11 p.m. until 7 a.m. And during the remaining times, the ventilation will simply operate for domestic use, so as not to introduce additional heat gains into the room from the ventilation air, and that this minimal ventilation was provided. 100,000. 100,000. Yes, and now we've implemented our new model. We confirm and perform calculations, observing what happens on our temperature chart. Will we be able to achieve the specified temperature under absolutely any conditions below 32 degrees Celsius, or indeed equal to that? Here we can also turn off the parameters for the external and supplied air, which are currently equal in this specific situation, so we can observe what's happening. Well, here it's visible. We have a slight temperature overshoot. My apologies. The permissible 32.26 degrees Celsius, so it will probably still require a slight increase in the amount of air, but I'm assuming that for the purpose of this video I won't be correcting it. So in this way we can easily understand heat accumulation in equipment and partitions to perform calculations. Here we have a graph of the relative humidity showing us how the relative humidity in the room will change, and similarly we have the anhydrous moisture content, and here we also have the heat balance chart. Here these blue lines in this particular situation are showing us the power output capabilities concerning the actual free cooling that is being achieved. And moisture balance. Well, in this particular situation, there's not much to interpret because we're directly introducing outside air. We can, of course, export such results.
Regarding the computational report.
This is what the situation looks like.
All the input data has been thoroughly introduced here, along with the comprehensive results and a detailed legend that provides full descriptions for every single variable that is actively involved and participating in this specific simulation. And generally, when it comes to these types of calculations, that's everything. You yourselves can make all sorts of modifications, experiments, and so on right here. I'd like to thank you very much for your attention, and I'll see you in the next video. Bye.